Okay, so for this video we're going to talk about Newton's second law in rotation. We talked a little bit about this already. We introduced some of the concepts using torque and moment of inertia and angular measurements, and so this is going to focus on more examples on how all of that tends to come together. So to start with a little bit of review, let's think back to just Newton's second law for net force is mass times acceleration. I want to do a quick example with this one just to kind of show how all of it's still going to be used and relevant even though we're converting now to rotational of net torque is moment of inertia times angular acceleration. So let's start with an example involving no rotation. Now you may remember this example that we've done back when we started with forces. The idea is pretty simple. We'll have two boxes. One box is sitting on top of the table and it's attached over a pulley to another box, and we'll call these boxes M1 and M2. Now to make this easy, we'll say that the surface is frictionless. We don't need to make this more complicated than it already will seem. And since there's no rotation, we'll consider the pulley to be massless. Now hopefully you remember how to do most of this, so I'm going to go quick, but hopefully you can follow pace because this should be a review. So we start by making our free body diagrams. So for mass 1, it's basic. You got tension pulling it to the right. We have a normal force pushing up from the surface. We also have gravity pulling down on that box. For mass 2, we have tension pulling it up, and we have gravity trying to pull it down. Now keep in mind, because the pulley is massless, our two tensions are the same thing. Because it's the same piece of string over the massless pulley, the FTs are the same in both these diagrams. So let's write out our equations for both masses. Mass 1 is pretty easy. Tension is the only force that's going to cause motion, so that's equal to ma. For mass 2, there's two forces. Now we're going to change this up a little bit. You'll notice that I'm saying the tension is negative and the weight is positive. And that's because I'm choosing the positive direction to be whichever way I know it's going to accelerate, in this case downward. So the weight should be in the positive direction and tension would be negative. So to solve this for the acceleration, one of the tricks we can use, which will prove more useful when we start adding rotation, is let's combine these equations by simply adding both sides. So we'll add the left side together and we'll add the right side together out of these two equations. You should see that because the tension is both positive and negative on the left side, those will drop away and we're left with just the weight, mass 2 times gravity. On the right side, these will combine, mass 1 times acceleration plus mass 2 times acceleration. And to solve this, it's pretty basic. We're going to factor out the m's and divide them to the other side. So mass 2 gravity divided by mass 1 plus mass 2 is equal to the acceleration. Hopefully this expression is familiar to you. Now I want to draw your attention to something specific about this equation. First, it's to notice that on the top, the mass 2 times gravity, this is the only force in the system that's causing the entire system to move. So we consider this an external force. So all the forces in the problem, this is the only one that causes movement. The tensions are considered internal forces. And thanks to Newton's third law, all internal forces cancel. So all we care about is the external force to the system. And on the bottom, you'll notice that m1 plus m2 represents the total mass of the system. More importantly, this is the effective mass. Now that's an important idea to understand because what it means is whatever the net external force is, it's pulling on whatever the effective mass of the system is. In this case, the total mass. So remember that as we get to our next part. So now what do we do if the system or the object itself has rotational aspects to it. Now, we've already discussed forces, and we know the ideas that cause rotation, such as torque, moment of inertia, and things like that. So now let's put it all together. So we'll start with a quick example. Suppose we have an object like a disc, wheel, something that rotates. Okay, so we'll call this a disc. It has some mass to it, and this disc is wound up by a string. Maybe attached is the wrong word, but you get the idea. The string is wrapped around this disc and it's attached to the ceiling. So we know once we release this disc that has some mass to it, say just mass m, once the disc is released, the string is fixed to the ceiling. So the disc will begin to rotate as it falls. Now that's important because understand that that's what makes this different. Not only is it rotating, but it's also falling. So we have linear motion as well as rotational. Now, because this object has mass, it has a moment of inertia, and we know that gravity is the force that pulls it down. So let's start with the basics. Free body diagram. We've got two forces. We've got tension pulling up on the disc, and we have gravity pulling down on the disc. Now, I know in the picture, tension's not quite acting at the same point that gravity is, but it's still a force trying to pull up on the disc. So when we write out our net force, same thing we did in the previous example, mass times acceleration is equal to gravity minus the tension. Again, notice the signs. It's falling, so I know the net force is downward. So that means anything downward, I'm going to consider the positive direction. But you also notice there's two things that we don't know in this equation. We don't know the acceleration, and we don't know the tension. So we have to look at it from another perspective. Here's where the rotation comes in. So if we look at the net torque acting on the system, that's moment of inertia times the angular acceleration, the only force causing torque is tension. So our net torque is 1 torque, radius times tension. We also know expressions for the other items. We know the moment of inertia is 1/2 mr squared. But what about the angular acceleration? Well, remember, when there's no slipping, we have an expression for that. That the linear acceleration a is equal to the radius times the angular acceleration. So a quick solve for the angular acceleration gives us the linear acceleration divided by the radius. Now from here, we're going to do a little bit of algebra. On the left, we'll see that one of those r's is going to cancel. So we're left with 1/2 mass radius times the acceleration is equal to radius times the tension. Final step would be to divide off the radius on both sides, and we get that the tension is equal to 1/2 mass times acceleration. Now we're going to do the same trick that we did in the previous problem. We're just going to take these two expressions and we're going to add them together. The net force acting on the object and the net torque acting on the object. So now if we add both sides together, we'll see that on the right side, just like in the previous example, the two tensions are opposite in sign, so they're going to cancel. Again, tension's an internal force, so it contributes nothing to the overall external force of the system. So now when we add together the left side, mass acceleration plus 1/2 mass acceleration, it's equal simply to the force due to gravity pulling down on the disk. Now by factoring out the acceleration, we can solve for the acceleration by simply doing the force due to gravity, mg, divided by m plus 1/2 m. Again, remember what we referred to in the last example. On the top, we see that this is the net external force. It's the only force actually causing a change in what's going on in the system. And on the bottom, we have the effective mass. It's the mass of the disk m plus the effective additional component because of its rotation. And that's important. That rotational part adds mass. And you'll notice that the 1/2 mass was simply the rotational inertia component. So what does it take to actually go through and solve rotational dynamic problems? If you didn't catch on to the previous two examples, we're going to list it out here, and you should see that the process is pretty simple. First, start with your free body diagrams. You have to be able to identify the forces. You have to know what's going to cause motion, what's going to cause rotation, and best place to start is your free body diagram. And it's important to make sure you make a free body diagram for every mass in the system. The second step is to simply write out your net force equations for any object that's moving in a straight line. The next thing is to look at any object that is rotating. And if it's rotating, then there must be torques causing that rotation. So identify what forces are causing torques on that object. Then you're going to use those torques to set up your net torque equation, which is Newton's second law in rotation. Net torque is moment of inertia times angular acceleration. Next, remember that if there's no slipping, which is typically the case, and every once in a while they'll throw this in there too, just to check if you understand, but if there is no slipping, then the linear acceleration is equal to the radius times the angular acceleration. Now once you've done all your algebra within your net torque and net force equations, remember to combine these two. Add the net force and the net torque together. This will eliminate any of the variables that are internal to the system and don't really contribute to the overall motion of the system. And finally, solve it. Typically, it's for the acceleration. So now let's do an example that combines all of this information. So we're going to return to our previous example, what we started with. Two masses connected by a string hanging over a pulley. This time, however, the pulley has mass. And if the pulley has mass, it has rotational inertia. So there is rotation here, and we need to account for that. And pulley typically is like a disk, which we've already used. Moment of inertia is 1/2 mr squared. Now we'll keep the surface of the table frictionless, because again, do we really need to make it more complicated than it's already going to seem to be? So going back to our list of steps to solve this problem, let's start with our free body diagrams. So there's three objects here, and we'll start with mass 1. Mass 1, we know there's a normal force pointing up, there is weight on mass 1 pulling it down, and there's also a tension pulling it to the right. Now you'll notice that I labeled this tension FT1. That's important, because for mass 2, when we make its free body diagram, it has a tension pulling up, and then we're going to label that tension FT2. These tensions are not the same anymore. If the mass, or the pulley rather, has mass, we cannot say that the tensions are the same, because each mass is trying to rotate the pulley differently, and therefore these are different tensions. So when we look at the free body diagram for the mass of the pulley, you see that there are two forces trying to rotate this pulley in different directions. So again, you cannot make the tensions the same. So let's go ahead and start making our net force equations. So for mass 1, it's pretty easy. Tension 1 is going to cause acceleration. So tension 1 is equal to m1a. For mass 2, again, keep in mind the directions. We know the net force is going to be downward. That's the way it's accelerating. So that means gravity, mass 2 times gravity, is positive, and the tension 2 is negative. Now what about torques? Now I know we talked about the sign convention for torques, but do the same thing here. Which way is it going to rotate? And in that case, tension 2 is what's going to cause the rotation. So tension 2 will be positive, and then tension 1 would cause negative torque. Again, just think about it as which torque is going to cause it to rotate that way. And because of the way M2 is going to fall, torque 2 is actually the torque that's going to cause rotation. So let's substitute our expressions. The moment of inertia is 1/2 mass of the pulley times the radius squared. We already knew that expression. It's not slipping, so we know the angular acceleration is linear divided by r. And on the right side, we have our two torques. So let's do some algebra here. Now after you do your steps, you're going to see that all the r's are going to cancel. So we're left with 1/2 mass of the pulley times the linear acceleration is equal to tension 2 minus tension 1. So then the next step, remember, is to take this equation and add it to all of our net force equations. So we've got 3 equations here, and let's just add all the way down. Now on the right side, notice the tensions. There's a positive and negative tension 2, and a positive and negative tension 1. So all of our tensions are going to cancel. And again, tensions are internal to the system. They should cancel. So the only force causing any kind of movement here is the gravity acting on mass 2. And on the left side, we've got 3 things to add together. Mass 1 times acceleration, mass 2 times acceleration, and half the mass of the pulley times the acceleration. So when we solve this for acceleration, we can factor out all of the m's, and to isolate the acceleration, it'll be mass 2 times gravity divided by m1 plus m2 plus half of the mass of the pulley. And again, see how this makes sense. The only force causing movement is gravity acting on mass 2. That's the only external force. And on the bottom, we have the mass. More importantly, the effective mass. The effective mass of the system is both mass 1 and mass 2, plus the effective mass of the pulley. Again, because the pulley is rotating, it contributes a small amount of mass to the overall system. Hopefully that made sense. I know it's kind of a lot to take in, but tomorrow be prepared to do some more practice with this in class. If you've got questions, bring them to class. We'll talk it through. You'll find that for the most part this isn't too complicated. Hopefully this video made it clear. Watch it again. Watch as many times as you need. Take notes on it. Bring your questions tomorrow and be prepared to do some practice. See you then.